Welcome to this recap video on continuity, which is section 17 of Ross. So the perspective that we're really taking in this class is one of sequential continuity, which is to say that we can pass a limit through a function. If we can, then it's continuous at a point. So a function is continuous at a point x naught, and that point is in its domain. If for every sequence in its domain that happens to converge to x naught, so in this case, you could say that x naught is equal to the limit of xn, then you have that the limit of xn, limit of f of xn is f of x naught, which you might then write as this: the limit of f of xn, the limit of the sequence of function values, is equal to the function of the limit, right? Because this is x naught, as we wrote there. So that's what I mean by passing a limit through a function. That's what we mean by continuity. And this is a nice definition as far as our definitions go, because there's really just two steps to it. The first step in any proof is to say, let xn be in the domain of f such that xn converges to x naught. And then step two, show that the sequence of function values converges to the function value at the limit, x naught. And you typically will just use limit theorems to prove that. So we show in this theorem 17.2, which was gone over. I proved this in class. I'm not going to go over the proof in this video because it's rather detailed and you can find the proof in the text. But we proved it's equivalent to the epsilon delta definition or characterization of continuity that you might be more familiar with, which is to say, for all epsilon greater than 0, there exists a delta greater than 0, such that for every point in the domain that is within a delta distance of x naught, the difference in the function values is within that epsilon distance of f of x naught. So that's probably something you're more familiar with from calculus. This is something that Josh talked about, and so I'm not going to relitigate things, but there are the pictures, and the ideas of the proof are something that are in these notes, and we went over the proof carefully. So the one thing I just want to emphasize is just how nice the proof is for continuity from the sequential perspective versus the epsilon delta in general. So as one example, if you looked at proof of 17.3, here you say, well, let f be a real valued function with its domain some subset of the reals, and we say it's continuous. If it's continuous at a point in its domain, then the conclusion is so is the absolute value of the function, and so is some scalar multiple of the function. Those are also continuous functions at x naught. And this is how long the proof is. So there's two conclusions to this, and this is how long the whole proof is for the sequential continuity. So here's that step one, is you let xn be in the domain of f, a sequence in the domain of f, such that x sub n converges to x naught. So that's step one. That's what you always write. And then you go on to step two. And this is step two for the absolute value function. I say for standard results, if y sub n converges to y naught, then the absolute value of yn converges to absolute value of y naught. And these were details I went over in exercise 17.7 in class. So I won't go over them again here, but that's a sequential result that we prove. And so that means that f of xn being the kind of corresponding yn values, and f of x naught being like the y naught values, since they converge, then you have that their absolute values converge. The absolute value of f of xn converges to the absolute value of f of x naught. So I'll try to clean this up a little bit. So that gives you the continuity. That's it. That's all you got to do for continuity. And then similarly for kf, like we know this result, this is a limit theorem, right? By a theorem, kyn converges to ky naught if yn converges to y naught. And since we said f is continuous, we know that f of xn converges to f of y naught. Then by the same sequential limit theorem, kf of xn converges to kf of x naught. And that makes this kf continuous. So that's why I like these sequential continuity proofs. They're really short. They're nice and clean. They're just building on the previous results we developed for sequences of real numbers. The epsilon delta, I'll kind of let it stay up here. This is the whole thing in its entirety. You can pause the video. I can't recall if I gave this in the notes for you or not, but it's quite a bit more detailed. You let epsilon be greater than 0. There's like that first step up here, and it's one epsilon for the whole proof, so I just write it once. And then I explain how you choose delta 1 for the absolute value function, and then show how everything works with the epsilon delta for that. So this is the proof of the absolute value of f being continuous, and this is the proof of kf being continuous, which is just quite a bit longer than this. That sequential continuity. As far as activities examples go, we played with, understanding domains and compositions of functions. And then there was this idea of using these standard set of results. These are theorems that you should be familiar with. They're really just direct analogs of what we've seen for the most part from sequences back in like section 8, section 9, primarily in chapter 2. The only one that's a little bit different is theorem 17.5. You should be able to do the proofs for every single one of these. They should be short, and they should just be using limit results from sequences of real numbers. So I proved 17.3 above. We provided an alternative one to that in class in terms of showing the absolute values being continuous. And then 17.4 and 17.5 you should be able to prove. And you should look at the proofs in the book, but you should be able to do them for yourself. Then applying the theorems is really nice to prove that whole sorts of complicated looking functions like this one, log base e of 1 plus cosine to the 4th of x, is also continuous. So let's see, what else is there to do? Again, here's a sequential proof. If Sn is a sequence of non-negative real numbers, then we should be able to show that, or excuse me, that was the example that we're using. If we want to show the absolute value of x is continuous on its domain. So this is a little bit different because we're not specifying continuity at a point, we're specifying continuity on a set of points. And so the only thing that changes in the proof there is this first step right here where you say, well, let x, or you can maybe say x naught, but let x be a point in this domain. And so now it's arbitrarily, but it's chosen, it's fixed. And then you let x in be some sequence. So this is kind of like a step 0 because you haven't specified it, actually proving continuity on the domain. So you say, well, pick a point in the domain. I don't care which one. And now the first real step in the proof is, well, pick a sequence. Here's step 1. Make that one a little bit better. Step 1. Pick a sequence in the domain that converges to that point in the domain. I don't care which sequence, but it's any sequence that converges to that domain. And then show me that the sequence of function values converge. And there we're just using example 5 from section 8, which gives us the result. Again, sequential proof of continuity, very nice. We did induction for 17.5 along with some of those theorems that I was just highlighting to prove continuity of all polynomials. Then 17.7 was one we did to basically give an alternative proof of that theorem 17.3. And let's see, we did some scratch work for 17.9 and 17.10 in terms of epsilon delta and sequential characterizations of continuity. And so then the longer proof of this exercise is one that we haven't done. So I'm going to make a separate video actually for this exercise because it's a little long to go through. So I'll stop this video here and then I'll create another one that just goes over exercise 17.14. So thanks for listening to this, and I'll talk to you in the next video.